Hi everyone. Now I am here with a presentation on topic CANNY edge detection algorithm. Now let's check what is this edge detection refers to. The edge detection refers to the process of identifying and locating sharp discontinuities in an image. Different methods of edge detection are available in computer vision. They are Roberts cross operator, Sowell operator, Prewitt operator, Laplacian of Gaussian filter, CANNY's edge detection algorithm. Here, I shall talk about most widely used edge detection algorithm gradient of Gaussian, that is the CANNY's edge detection algorithm. Let's check more about it. Yes, here comes why CANNY edge detection algorithm. We have considered CANNY edge detection technique with regards to following criteria. There are three criteria actually: detection, localization, number of responses. The first one is the detection. Let's check. The probability of detecting real edge points should be maximized, while the probability of falsely detecting non-edge points should be minimized. This corresponds to maximizing the signal to noise ratio. Then the localization. The detected edges should be very close to the real edges. There will be minimum gap between the real edge and the detected edge. And what about the number of responses? It actually means one real edge should not result in more than one detected edge. So that let's check what is the steps in CANNY edge detection algorithm. The steps are given below. They are mainly 5 sequential steps. The first one is smoothing, second one is finding gradients, third one non-maximum suppression, fourth one is the hysteresis thresholding. Here comes the first one. Images taken from a camera will containing some amount of noise. As noise must lead the result in finding edges, we have to reduce the noise. Therefore, the image is first smoothed by applying a Gaussian filter. This is actually set in the smoothing. Now let's check. The function Gaussian filter multiplies each pixel in the image by the kernel generated it. Returns the smoothed image in a two-dimensional array. The given are the equations S equal to I into g of xy equal to g of xy into 1, where the g of xy is the Gaussian filter function. And the given table is representing the discrete approximation to Gaussian function with the sigma equals 1.4. Now let's check the here comes the finding gradients. Let's check how we can find the gradients. Here we will find the edge strength by taking the gradient of the image. The Sowell operator performs a 2D spatial gradient measurement on an image. The Sowell operator uses a pair of 3x3 convolution maps. One estimating the gradient in the x direction and the other estimating the gradient in the y direction. Here it gives the mathematical representation of all Gaussian functions. Here comes the next one. So after determining the value, now the approximate absolute gradient magnitude, that is the edge strength at each point, can be found as g equal to square root of g square x by g square y, and the orientation of the gradient can be found using the gradient in the x and y direction. That is equals tan of minus 1 tan inverse into gx by gy. And next, here comes the non-maximum suppression. This is necessary to convert the blurred edges in the image of the gradient magnitudes to get the sharp edges. Actually, this is performed by considering only all local maxima in the gradient image and deleting everything rest. The algorithm is applied for each pixel in the gradient image. Finally, only local maxima have been marked as edges. The given are the representation of the normal detection to an edge. Here, the x dash and the x bar are the neighbors of x along normal detection to an edge. Next, we can move to the example of non-maximum suppression. The first one is the not suppressed image, and the second one is the suppressed image with it clearing all the clutters and the noise. And next, Yes, here it is a hysteresis thresholding. After the non-maximum suppression step, the edge pixels are still marked with their strength pixel by pixel. The result image may still contain false edge points. Using threshold, potential edges are determined by double thresholding, that is high and low. If the gradient at a pixel is above high, declare it as an edge pixel. If it is below low, declare it as a non-edge pixel. Between low and high, consider its neighbors iteratively, then declare it an edge pixel if it is connected to an edge pixel directly or via pixels between low and high. Now yes, here comes the gradient magnitude history thresholding the mapping, how the high and the low levels are marked effectively. And now let's check the next one. Here basically they are discussing about the performance of CANNY edge detection algorithm, how they are performed and all. The high and low sigma also controls the sizes of the Gaussian filter. The bigger value of a sigma, the larger size of the Gaussian filter comes, which is inversely proportionally equals. Thus implies more blurring necessary for noisy images as well as detecting larger edges. As expected, however, the larger the scale of the Gaussian, the less accurate is the localization of the edge. Smaller values of sigma imply a smaller Gaussian filter, which limits the amount of blurring, maintaining finer edges in the image. And finally, CANNY's edge detection algorithm is computationally more expensive compared to Sobel, Prewitt, and Roberts' operator. However, the CANNY's edge detection algorithm performs better than all these operators under almost all scenarios. So that it can be concluded as all the smaller values and this performance of the CANNY algorithm depends heavily on the adjustable parameter sigma, which is the standard deviation for the Gaussian filter, and the threshold values. So that's all for the CANNY edge algorithm. Thank you for your patience.